So we saw in the last section that you could tell whether a reaction was spontaneous in the forward direction or if it was spontaneous in the reverse direction just by calculating at least at standard conditions, whether the delta G at standard conditions for that reaction was negative or positive. But we can go further than that. It turns out that, first of all, that the temperature dependence of the delta H and the delta S is small compared to the temperature dependence of having the T right here. So we can look and see what's happening with the change in the Gibbs free energy by looking at enthalpy and entropy. In fact, if you know the signs of these, you can already tell whether this is positive or negative. See, delta H negative exothermic reactions contribute negative to this, and it makes delta G negative. And if delta S is positive, right, that tends to make this negative because of the negative sign in the front. Right? So if you have a reaction that you know is exothermic, like burning of ethane, and you know, that wasn't a good example, but you know that the entropy is increasing, right? So if this is negative and this is positive, then both terms are negative because of the negative sign here. So delta G has to be negative. You don't need to look anything up because you already know that some reactions give off heat or don't give off heat, or some reactions are endothermic, right? So if you have an idea if they're endothermic or exothermic, and whether delta S is increasing or decreasing because it's becoming more random, then you can kind of figure out whether delta G is positive or negative. And sometimes the signs of these are different. Right? So let me look at that on the next slide. So what this says is if enthalpy is negative, right? Change in enthalpy is negative, exothermic, and delta S is positive, then no matter what temperature you're at, you can change the temperature all you want, both these terms are negative. So it's always going to be spontaneous in the forward direction, regardless of temperature. It's always spontaneous. And the reverse is true. If it's endothermic, right, and you know that the entropy is negative, then both these terms are going to be positive, and it will always be spontaneous in the reverse direction. Right? Easy enough. Now let's look at the mixed cases. Right? If both enthalpy and entropy changes are negative, well then it depends on that makes this term, they're both negative, that makes this term negative, and this term is positive. Right? So one term is negative and one term positive. So whether the whole thing is going to be negative or positive depends on how big the temperature is. And at some low temperature, if T gets small enough, say set it to 0, then the enthalpy is going to dominate. Right? Enthalpy is going to dominate when the temperature is 0. Right? And so when enthalpy is negative, the delta G is going to be negative, and it will be positive. It'll be spontaneous in the forward direction. But when you go to high temperature, this second term is now dominant. Right? You can ignore this one. Well, this term now, negative for the entropy times the negative, this is a positive term. That means it's going to be spontaneous in the reverse direction. Right? And if you reverse the situation and you say they're both positive, then the result comes out that at low temperature, the reverse is spontaneous, and at high temperature, the forward is spontaneous. We're going to do some examples with this, but I want to first give you a warning, and I've seen students that try to memorize this or something. I wouldn't suggest that. The better thing is just to memorize this equation, right? Or you don't even have to memorize that. It's on that equation information sheet. And you can figure all of this out. You can just figure it out by looking at the signs here. You just have to remember that delta G negative is spontaneous in the forward direction. Right? Much less to memorize. Don't bother memorizing this whole thing. Just remember kind of the result. If the signs are different, it's always going to be something, either always forward or always reverse. You can figure it out. And if the signs are the same, right, both negative or both, the signs are the same, then it's going to change depending on whether the temperature is high or low, and you can figure that out too. Just set the temperature to 0, and it's going to be the same as whatever the enthalpy is, and it's going to reverse at some intermediate temperature. All right, let's look at examples 9 through 11. Example number 9 says, assuming that the delta H standard conditions and delta S at standard conditions do not change with temperature, calculate the temperature for which delta G is equal to 0 for the reaction, which would then be the equilibrium, right? Because delta G is equal to 0, that's going to be the equilibrium. So remember, delta G is delta H minus T delta S. So if delta G is equal to equilibrium, then delta H is equal to T delta S. And if we're trying to solve for that temperature, then that temperature is going to be delta H over delta S. Right? And delta H is right there. It's 27.66 kilojoules. So kilojoules is times 10 to the 3 joules, because we have to get the units the same. And the delta S is 86.39 joules per Kelvin. So now the Kelvin's going to go into the numerator, and your answer comes out 320.2 Kelvin. Equilibrium, if this is carbon disulfide liquid going to carbon disulfide gas, that means that is the boiling point. That's the temperature. So this is the difference between the enthalpy between a liquid and a gas, and this is the difference between the entropy between the liquid and the gas. And you come up with, you ended up calculating the boiling point, the temperature, 320 Kelvin. Okay, that was number 9. Number 10, giving the following chemical reaction and data at 298 Kelvin, standard conditions, and again, assuming that delta H and delta S do not change much with temperature, calculate delta G at 1000 Kelvin. All right? It's not standard conditions. Not standard conditions. And by the way, when you look up in the book, this is what you find in many of these books. You'll have 3 tables. Maybe these are going to be the columns. You'll have the delta H's, the delta S's, and the delta G's for each of these elements. So I've just put them in, this is kind of a table here. So the nitrogen, delta H is this, and delta S is this, and delta G is this. So this is what you'd find in the table. So anyway, why don't you pause the video and see if you can figure this out, and then turn it back on, and we'll see whether we can do this. Okay, so it would be easy enough if you were asked for what is delta G 0 at standard, whoops, yeah. Well, this really shouldn't be delta G 0. It should be just delta G. Maybe there shouldn't be a little 0 though. Delta G at 1000 Kelvin. It should just be delta G. But anyway, if you were doing it at standard conditions, you would just do delta G equals, it would be the sum of, the sum of the reactant products minus the reactants. Right? But we don't want it at standard conditions. So instead we're going to use this equation. Delta G is delta H minus T delta S. All right? And again, we're assuming that these are not going to be temperature dependent. Okay, even though we're going to change the temperature. So, so if you look up delta H is going to be 2 times ammonia, right? Delta H, right? For this reaction is going to be 2 times negative 46.1, right? Which ends up being that's 2 moles, so that's negative 92.2 kilojoules. And delta S is going to be 2 times 192.3, because that's the ammonia value, and then minus minus 191.5 for the nitrogen, and also minus 130.6 times 3. And I think if you work that out, you end up with negative 198.7. And that's going to be joule per Kelvin. So you've calculated delta H and delta S for this reaction at standard conditions. So now, I really shouldn't have an F here. These are for the reactions. So now the delta G for the reaction is going to be negative 92.2 kilojoules plus, or I can say minus T delta S. Temperature is 1000 Kelvin, and delta S is 198.7 joules per Kelvin, which this just makes this, the 1000 turns this joules into kilojoules. So you have to turn this, why does it happen all the time? Turns the second term into kilojoules by just multiplying it by 1000, and you'll end up with 106 positive, because this is 198.7 kilojoules, this is minus 92.2 kilojoules, you get 106.5 kilojoules. All right, so you couldn't just use these delta G values here at all. You had to get the temperature dependence, because we were assuming that it was delta H and delta S that didn't change with temperature. The temperature dependence came in the T. All right, that's where the temperature dependence came in. All right, so number 11, there's one more. You can try this one. Calculate the standard Gibbs free energy change at 298 K using only the standard free energies of formation for this reaction. This looks actually like an easier calculation than the last one. Maybe we should have done 11 first. But why don't you try to pause the video, do this calculation, and then turn it back on. Okay, so this is we're doing this at standard conditions, so you don't need to use delta S or delta H, even though they're in the tables, right, as they are in the back of the book. We can just do this with the delta G. So the delta G for this reaction is going to be 3 times the N2H4. N2H4 was 149.24. And then we subtract from that 4 times the ammonia, and ammonia was negative 16.48. And looks like nitrogen is 0 because it's an element, so we can just do that part of the calculation, and you end up with 514 kilojoules. I should really do this calculation first. Oh, wait a minute. I see why it's second. All right, there's a B part. That was an A part. How about a B part? Now try to do it at 350 Kelvin. Okay. Do it the way we did the last problem. Do it at 350 Kelvin. Pause the video. I think, so now, again, this time we're going to find delta G for the reaction. For this reaction is going to be the delta H for the reaction minus T times delta S for the reaction. So, and the delta H you figure out in the way that you always do. This time we have to use the element, the things that I crossed out here. All right. So delta H is 3 times the N2H2 which is 50.63, 50.63 times 3. And then we're going to subtract 4 times the ammonia, which is negative 46.11. And that comes out to, this is positive, this is both positive terms, it ends up coming out to 336.33 kilojoules. Delta S, you do the same thing, except there's more terms in it. It's 3 times the N2H4 again, which is 121.21. Right. Minus 4 times the ammonia, 192.3, and then 1 times the nitrogen, 191.5. And that comes out to negative 597.07 joules per Kelvin. Joules per Kelvin. So delta G is 336.33 kilojoules minus T, which is 350 Kelvin, times negative 597.07 joules per Kelvin. So remember, you've got kilojoules here and joules here. So if you want them both to come out in kilojoules, one thing you can do is just move this decimal place 1, 2, 3 places over. Put 0.350 in your calculator instead of 350, and this will turn into kilojoules. And then you can, everything's in kilojoules, and you'll end up with 545. So from 298 to 350, it went from 514 kilojoules to 545 kilojoules. It changes with temperature. Okay,